Let's look at some radical expressions. Now, the thing here again is algebraic principles and some evaluation. So the main things that you need to know about radical expressions is number one, there's not a lot of algebraic properties that work with them. The two main ones that we have to work with are that if you have two items multiplied underneath a square root or cube root or any kind of root, um, you can split that up into two separate square roots that are multiplied, or cube roots, or fourth roots, whatever the case may be. If you have a fraction underneath a root, you can split that up into two separate roots that are divided. Okay, so you can work with those kinds of principles, and these go in reverse as well. So if you have two roots that are multiplied, you can combine them into a single. Now, the things to watch out for. One of the most common mistakes I see students doing with radicals is trying to do the same thing for addition and subtraction. However, this is not the case. You do not have these principles to work with. So if you have two things added underneath a square root, unless you can factor it and then that factor happens to be a perfect square or whatnot, like there's not much you can do. You just leave it alone. That's really the biggest thing. All right, so these are pretty common. If you have something underneath a root, whether it be a square root, a cube root, or whatever, you can simplify values. So for instance, like 108 is not a perfect square. However, it may have factors that are perfect squares. And you might not know what those factors are right off the bat. But for instance, let's see here. I know 108 is 54 times 2. All right, well, 54 and 2, neither of those, I'm not aware that either of those are perfect squares. All right, so let's keep trying. So 54 is even, so there's another factor of 2. So I could write this as 27 times 2 squared, which is 4. I'll just go ahead and write it as 4. So 108 is the same thing as 27 times 4. And then also, 27 I recognize as 3 cubed. So I could write that as 3 squared times 3 times 4. And here's the thing. The 3 squared is a perfect square. It can come out of the radical as a single value. 4 is a perfect square. It can do the same. Everything's multiplied, but this would end up being 3 times 2 times the square root of 3, which would be 6 square root of 3. Now, if you recognized 108 as some number times 3, you would have seen that perfect square right off the bat. You would have done this in one shot. However, not everybody sees them, immediately. You can kind of break them down bit by bit is the whole point. But you can reduce them. All right. The square root of 16b to the 5th. Well, 16 is a perfect square. I can just go ahead and pull that out as 4. You can pull it out under the radical as long as you go ahead and take its square root. B to the 5th is not a perfect square because it's not an even index, but I could write this as 4 times the square root of b to the 4th times b. B to the 4th is a perfect square, all right, because it's an even power. So that would be b squared times the square root of b. So if you can reduce that. If you're dealing with cubes, you just need to pull out 3 factors at a time. So for instance, I could rewrite the stuff underneath here. 8 is the same thing as 2 cubed. X to the 5th could be written as x cubed times x squared, and then I have y cubed. All right, so 2 cubed, that's a perfect cube. I'm looking for perfect cubes. It comes out as just 2. X cubed comes out just as x. And then the y cubed comes out as just y. But those all come out, but I still have this x squared underneath the radical. I have to leave it. I can't pull it out. All right. If I had fractions, then the same sort of thing would occur here. I could write, let's say, this as x to the 4th times x over the square root of, and let's see, 54 I don't necessarily recognize as anything that's got perfect squares in it, but I do see 54 as, say, 6 times 9, and then 9 is a perfect square. So x to the fourth could come out as x squared. And then I have here the 9 could come out as 3. And this may or may not be the final form that you want to leave it in. Sometimes textbooks might say like you can't leave a denominator that has a square root in it. It doesn't really make a whole lot of difference in the end. It's an equivalent answer. That's usually something what we do a lot for trigonometry and not necessarily calculus. This is fine for our purposes. As long as you understand the algebra involved, that's the important part. All right, so as I mentioned, we need to be able to change formats. So like sometimes we'll have something written as a rational exponent. Sometimes we'll have a index, so like the root notation, the radical notation. We need to be able to change those things. So the nth root of a is the same thing as a to the 1 over n power. And that's often the one that gets used. But if you have like, you know, a real fraction, so like 2/3 or something, then the denominator is the index of the root, and the numerator is an exponent, just as normal. And what's nice is that exponent can be underneath the radical or outside of the radical, and it doesn't really matter. It's just kind of what's ever easier for you under the given situation. All right, so for instance, 25 to the 1/2 power is the same thing as the square root of 25. The denominator makes the index, so the index is 2, so it's a square root. And, well, square root of 25 is 5, so 25 to the 1/2 power is just 5. 32 to the 3/5 power may look a bit more intimidating, but the 5, the denominator value, is the index of a root, and then the 3 is an exponent. All right, now 32, that's the same thing as 2 to the 5th power. So it's a perfect fifth, which means that, you know, the 5th root of 2 to the 5th would just be 2. So this is really 2 to the 3rd power, which is 8. So that just reduces nicely down to simply 8.